You're checking your weather app for the third time today? They read the sky like a book, without satellites, without radars, without a single instrument. Just wind, clouds, and centuries of observation. The Bedouins didn't just survive the desert's moods. They predicted them. Who needs meteorology when you have the desert itself as your teacher? For generations, Bedouin tribes across Arabia, the Sahara, and the Levant developed weather forecasting systems more accurate than many modern predictions. They could sense sandstorms 3 days before they hit. They knew exactly when the brief rains would come, and when the killing heat would follow to NO weather stations. No atmospheric pressure readings. No computer models. Their instruments were their senses, their animals, and the subtle signals that nature broadcasts to those who know how to listen. In a place where a wrong prediction could mean death, they developed an accuracy that would impress any meteorologist today. The desert doesn't forgive mistakes. A single miscalculation about incoming weather could wipe out an entire caravan. Caught in a sandstorm without shelter, travelers would suffocate within hours as fine dust filled their lungs and blocked out the sun completely. Surprised by flash floods in normally dry wadis, families would watch helplessly as their entire world was swept away in minutes. Missed the signs of an approaching heat wave, and dehydration would claim the week before nightfall. This wasn't casual observation. It was a matter of life and death science, refined through thousands of years of trial and error. Every generation of Bedouin weather readers built upon the knowledge of their ancestors, adding new observations, correcting old assumptions, and developing increasingly sophisticated prediction methods. The elders who could read the sky most accurately became the most valuable members of their tribes, their knowledge literally worth more than gold in the harsh economics of desert survival. But their forecasting went far beyond simple weather awareness. These nomadic meteorologists could predict the complex chain reactions that different weather patterns would trigger across the desert landscape. They knew which distant rains would fill specific oases weeks later. They could forecast which seasonal wind patterns would bring the plant growth that would feed their herds. They understood how weather changes in one region would affect the availability of water, food, and safe passage routes hundreds of kilometers away. Modern meteorological services, with all their sophisticated technology, still struggle to match the local accuracy these traditional forecasters achieved. Satellite images showed general weather patterns across vast regions, but Bedouin weather readers could pinpoint exactly which valley would receive rain, exactly when the wind would shift direction, and exactly how long dangerous conditions would last. Their predictions were hyperlocal and incredibly precise. The difference between knowing that storms are coming somewhere in the region and knowing that dangerous weather will hit your exact location at sunset tomorrow. The foundation of their system was understanding that weather in the desert follows different rules than weather in other climates. In temperate regions, weather changes gradually and follows relatively predictable seasonal patterns. Desert weather is violent, sudden, and extreme. A morning of perfect calm can explode into a killing sandstorm by afternoon. Months of drought can end with floods that reshape the landscape overnight. Temperature swings of 40 degrees Celsius between day and night are normal. In this environment, general weather knowledge isn't enough. You need precision forecasting or you die. They developed this precision by treating weather prediction as a full-time profession. While modern people check the weather occasionally and then go about their business, Bedouin weather readers were constantly monitoring, constantly analyzing, constantly updating their forecasts. Every breath of wind was evaluated. Every cloud formation was cataloged. Every animal behavior was noted and cross-referenced with atmospheric conditions. This wasn't a hobby or a side skill. It was their primary occupation and their greatest responsibility to their community. The stakes made them incredible observers. They trained themselves to notice changes so subtle that most people would never register them. A shift in wind temperature measured in fractions of degrees. A change in air pressure felt only as a slight sensation in their joints. A variation in humidity detected through the way sand felt beneath their feet. These tiny signals, invisible to casual observers, became the building blocks of remarkably accurate weather forecasting. But perhaps most importantly, they understood that weather prediction in the desert required reading multiple information sources simultaneously and synthesizing them into comprehensive forecasts. No single indicator was sufficient. Wind patterns had to be combined with animal behavior, Cloud formations had to be analyzed alongside atmospheric pressure changes, and celestial observations had to be integrated with ground-level phenomena. They developed sophisticated mental models that could process dozens of variables at once and extract accurate predictions from seemingly random natural events. This multifaceted approach created forecasting systems that were both incredibly reliable and remarkably adaptable. When conditions changed or new patterns emerged, experienced weather readers could adjust their methods and maintain their accuracy. They weren't just following memorized rules. They were applying deep understanding of atmospheric physics, even if they didn't use modern scientific terminology to describe their knowledge. The result was a weather forecasting tradition that kept entire civilizations alive in one of the world's most challenging environments. Without their ability to predict and prepare for extreme weather, the great trade routes across the Sahara and Arabian deserts would never have existed. The cultural exchanges that shaped medieval Africa, Asia, and Europe depended on Bedouin weather readers who could guide caravans safely through landscapes where one wrong forecast meant death for hundreds of people that lie in the desert. Wind isn't just air moving. It's a messenger. Every shift in direction, every change in temperature, every variation in moisture tells a story about what's coming. The Bedouins learned to read these messages with surgical precision. They recognized dozens of different winds, each with its own name and meaning. The Samum, a hot, dry wind from the south that could kill a man in hours if he couldn't find shelter. Its approach was marked by a peculiar stillness that would settle over the desert just before the killing heat arrived. Experienced Bedouins could feel the Samum building from over 100 kilometers away, sensing the atmospheric disturbance through subtle changes in air pressure that made their ears feel slightly blocked. The Khamsin, the 50-day wind, that brought dust storms and respiratory illness during the transition between seasons. Unlike the sudden violence of other desert winds, the Khamsin announced itself days in advance through a gradual yellowing of the horizon and an unusual behavior pattern in desert wildlife. Birds would fly lower than normal, seeking cleaner air closer to the ground, while insects would disappear entirely from areas that would soon be scoured by dust-laden winds. The Shamal, a steady northwesterly wind that cleared the air and promised cooler weather, but only if it arrived at the right angle and intensity. A true shamal came in steady, consistent gusts that gradually increased in strength over several hours. False shamala, winds from similar directions, but with different atmospheric origins, would start strong but fade quickly, often followed by even more intense heat. Distinguishing between true and false shamala required feeling not just the wind's direction and strength, but also its texture and temperature progression. But it wasn't just about direction and named wind patterns. Bedouin weather readers developed an extraordinary sensitivity to temperature changes in moving air, changes so subtle that modern instruments would barely register them. They could detect temperature variations of less than 1 degree Celsius by letting wind flow over their exposed skin and noting how it affected their perception of heat and cooling. A slight warming in an afternoon breeze that should have been cooling meant rain within 48 hours, as moisture-laden air from distant storms began infiltrating the local atmosphere. A sudden coolness in pre-dawn air, when temperatures should be at their daily minimum, signaled an approaching heat wave. This seemingly contradictory signal occurred because incoming high-pressure systems that bring extreme heat create atmospheric disturbances that temporarily cool the air before the main heat mass arrives. By recognizing this pattern, Bedouin forecasters could prepare their communities for dangerous temperature spikes days before they occurred. They trained their skin to become a sophisticated meteorological instrument. Different parts of the body were used to detect different atmospheric conditions. The face and neck, with their dense concentration of nerve endings, could sense humidity changes and electrical charge variations. The arms and hands were used to feel air pressure differences and temperature gradients. Even their scalp became a weather detection tool. Hair would respond to electrical charges building in the atmosphere hours before lightning storms or major wind events. The most crucial skill was predicting sandstorms, the desert's deadliest weather phenomenon. A Bedouin weather reader could feel the electrical charge building in the air up to 3 days before a major sandstorm arrived. This electrical buildup created a subtle tension that made hair stand slightly on end and caused camels and other animals to grow increasingly restless. The sensation was so faint that it required years of training to recognize, but experienced forecasters could use it to give their communities enough warning to seek proper shelter or change travel routes. They learned to recognize the eerie calm that preceded the most dangerous storms. Major sandstorms create massive atmospheric disturbances that actually suck air upward into the storm system, creating areas of complete stillness in advance of the horizontal winds that carry the deadly dust clouds. This stillness wasn't peaceful. It felt wrong to experienced desert dwellers, like the landscape was holding its breath before screaming. The duration of this calm period provided crucial information about the approaching storm's intensity and timing. A brief stillness of 30 minutes or less meant a relatively minor dust event would pass quickly. Complete calm lasting several hours indicated a major system that could last for days and reduce visibility to zero across thousands of square kilometers. The longest periods of pre-storm stillness, sometimes lasting most of a day, preceded the legendary sandstorms that could bury entire settlements and redirect the flow of major rivers. Modern meteorological research has confirmed the scientific accuracy of these traditional wind-reading techniques. Atmospheric pressure changes that precede major weather systems do create the exact patterns Bedouin forecasters learned to recognize. Electrical charge variations in the atmosphere do affect human hair and animal behavior in the ways traditional weather readers observed. Temperature gradients in moving air masses do follow the patterns they use to predict rain, heat waves, and storm systems. But the Bedouins went beyond simply recognizing these patterns. They developed sophisticated methods for interpreting complex combinations of wind signals. They understood that wind direction alone was meaningless without considering wind speed, temperature, moisture content, and the sequence of changes over time. A north wind in the morning followed by an east wind in the afternoon meant completely different weather than the same wind pattern occurring in reverse order. They could read the wind's memory, understanding not just where air masses were coming from immediately, but tracing their origins back through previous weather systems. Air that had passed over distant mountains would carry different moisture and temperature signatures than air from the same direction that had traveled over flat desert. Wind that had interacted with major storms hundreds of kilometers away would retain atmospheric disturbances that revealed information about weather patterns developing far beyond the horizon. This deep wind literacy allowed them to make weather predictions with remarkable accuracy and specificity, turning the constant movement of desert air into a detailed forecast system that kept their communities alive in an environment where the wind itself could kill. Animals were the Bedouins' living barometers, and the sky was their most reliable textbook. Together, these natural forecasting systems provided weather predictions more accurate than many modern methods, because they responded to atmospheric changes that human senses alone could never detect. Camels became the primary weather instruments for any serious desert traveler. These animals' extraordinary sensitivity to atmospheric pressure changes made them living early warning systems for dangerous weather. A camel's ability to detect pressure drops began roughly 18 to 24 hours before major storms arrived, when atmospheric disturbances were still too subtle for humans to notice. But their responses weren't random. Experienced Bedouin weather readers learned to interpret a complex vocabulary of camel behavior that revealed specific information about approaching conditions. When atmospheric pressure began dropping significantly, camels would become visibly agitated and refuse to lie down during their normal rest periods. They would pace in circles, make unusual vocalizations, and position themselves facing away from the direction of incoming bad weather. This wasn't instinctive behavior. It was a practical response to atmospheric pressure changes that made lying down physically uncomfortable for the animals. Bedouin forecasters learned that camels facing consistently in one direction meant dangerous weather approaching from the opposite direction. During extreme heat buildup, the atmospheric conditions that preceded the most dangerous temperature spikes, camels would seek shade earlier than usual, sometimes a full day before air temperatures began their climb toward lethal levels. They were responding to infrared radiation changes and atmospheric pressure variations that signaled the approach of high-pressure heat domes. A camel seeking shade at 8 a.m. when temperatures were still comfortable meant the afternoon would bring potentially fatal heat, giving human travelers crucial hours to find adequate shelter or change their route. But camels weren't the only animal forecasters. Desert birds provided even more precise timing for weather changes, particularly the rare and crucial rainfall that could mean the difference between life and death for desert communities. Pabara bustards, large ground-dwelling birds found across the Arabian and North African deserts, would begin flying in tight, low circles exactly 36 to 48 hours before precipitation arrived in their area. This behavior occurred regardless of whether clouds were visible, because the birds were responding to humidity changes and atmospheric pressure variations that preceded rain systems by days. Sand grouse provided different, but equally valuable forecasting information. These birds would gather near water sources in unusual numbers when extended droughts were about to break, somehow sensing that approaching rains would create temporary pools in normally dry areas. Their gatherings weren't random. They congregated at specific locations that would become water sources during rain events, demonstrating an understanding of desert hydrology that helped Bedouin communities identify the best places to position themselves for collecting precious rainwater. Ravens and other scavenger birds became indicators of sandstorm timing and intensity. These intelligent birds would disappear from open areas and seek shelter in rock crevices or deep vegetation 12 to 18 hours before major dust storms arrived. But their sheltering behavior varied based on storm intensity. Minor dust events would send them to shallow hiding places for short periods, while major sandstorms would cause complete disappearance for days at a time. Experienced weather readers learned to gauge storm severity by observing how thoroughly the scavenger birds vanished from the landscape. Even small desert creatures provided valuable weather intelligence. Scorpions would retreat deeper into their burrows before major temperature spikes, responding to ground temperature changes that preceded air temperature increases by many hours. Lizards would alter their daily activity patterns before pressure changes, becoming active at unusual times when atmospheric conditions were about to shift dramatically. But the sky itself was the Bedouins' most comprehensive and reliable weather forecasting system. They identified and named over 30 distinct types of cloud formations, each associated with specific weather patterns and timing. This wasn't simple observation. It was a sophisticated classification system based on cloud altitude, density, color, movement patterns, and interaction with local atmospheric conditions. Thin, wispy clouds stretching from east to west in parallel lines meant stable weather for days, as long as they maintained their parallel formation and didn't begin converging or breaking apart. These clouds indicated steady, high-altitude air currents that would prevent major weather system development. But identical clouds running north to south signaled imminent change, usually within 6 to 12 hours, because they indicated atmospheric disturbances moving perpendicular to stable weather patterns. Cloud color provided crucial information about weather timing and intensity. A slight yellowing of the horizon at sunset, caused by dust particles suspended in approaching air masses, meant sandstorms would arrive within 18 to 24 hours. The intensity of the yellow coloring correlated directly with storm severity. Pale yellow meant minor dust, while deep orange or red coloring warned of major sandstorms that could reduce visibility to zero and last for days. A green tinge in the pre-dawn sky was the most reliable predictor of desert rainfall. This unusual coloration occurred when moisture-laden air masses began interacting with the dry desert atmosphere, creating specific light refraction patterns that appeared only when significant precipitation was approaching. The green coloring would appear 48 to 72 hours before rain arrived, giving communities time to prepare water collection systems and adjust travel plans to take advantage of the rare moisture. Moon and star observations provided additional layers of weather forecasting precision. A sharp, clear moon with distinct crater details visible to the naked eye meant continued dry weather with minimal atmospheric disturbance. But a hazy or reddish moon indicated moisture in the upper atmosphere. Rain would follow within 3 days as the high-altitude moisture gradually descended and concentrated into precipitation systems. Star visibility served as a sophisticated humidity gauge that worked even when clouds weren't present. Experienced weather readers had memorized the normal brightness and visibility patterns of dozens of specific stars and constellations. When familiar stars appeared dimmer than usual, or when certain constellations became difficult to see clearly, it indicated increasing moisture in the upper atmosphere. They could estimate humidity levels and predict weather changes by noting which stars dimmed first and how quickly visibility deteriorated. The most skilled Bedouin astronomers could predict weather by observing the dancing of stars near the horizon. When stars appeared to twinkle or shift position more than usual, it indicated atmospheric turbulence that preceded major weather system movement. The direction and intensity of this stellar dancing revealed information about wind patterns and pressure changes occurring at altitudes far above ground level, providing early warning of weather developments that wouldn't reach ground level for days. This integration of animal behavior and celestial observation created a weather forecasting system that was both remarkably accurate and incredibly detailed, allowing Bedouin communities to prepare for specific weather events with precision that often exceeded modern forecasting capabilities. The most sophisticated Bedouin weather forecasting didn't come from instruments or even animals. It came from their own bodies. Experienced weather readers developed such sensitivity to atmospheric changes that they could predict weather through physical sensations, turning themselves into living barometers more accurate than many modern instruments. This wasn't superstition or folklore. Modern medical science has confirmed that human bodies do respond measurably to atmospheric pressure changes, humidity variations, and electromagnetic field fluctuations that occur before major weather events. But while most people experience these changes as vague discomfort or minor mood shifts, master Bedouin weather readers train themselves to interpret these physical signals as precise forecasting data. Joint pain intensified before atmospheric pressure drops, but experienced forecasters learned to distinguish between different types of joint discomfort that predicted different weather patterns. A dull aching in the knees and ankles meant general low pressure approaching, usually rainfall or moderate storms within 24 to 36 hours. Sharp, stabbing pains in finger joints warned of rapid pressure changes associated with violent weather, sandstorms, or extreme temperature shifts that could arrive within hours. Persistent shoulder and back pain indicated extended low-pressure systems that would bring multiple days of unsettled weather. The timing and intensity of joint pain provided crucial details about approaching weather. Pain that began gradually and intensified slowly over several hours meant weather changes would develop at a similar pace, giving communities time to prepare adequately. Sudden, severe joint pain warned of rapidly developing weather systems that required immediate action. Pain that peaked and then gradually decreased meant weather would arrive, reach maximum intensity quickly, and then pass relatively rapidly. Breathing difficulties served as an early warning system for dust storms and extreme heat events. Experienced weather readers would notice subtle changes in their respiratory comfort 12 to 18 hours before dangerous air quality conditions developed. A slight feeling of chest tightness or the need to breathe more deeply meant dust levels were beginning to increase in the upper atmosphere, even when ground-level air still seemed clear. More severe breathing discomfort warned of major dust events that would make outdoor activity dangerous or impossible. That respiratory changes weren't imaginary. They were responses to actual atmospheric particle concentrations and humidity variations that preceded visible dust storms. As distant sandstorms began moving toward an area, they would push microscopic dust particles ahead of them at high altitudes. Sensitive individuals could detect these particle increases through slight irritation in their respiratory system, providing early warning before dust storms became visible on the horizon. Sleep patterns became another layer of weather forecasting intelligence. Barometric pressure changes affected sleep quality in predictable ways that experienced weather readers learned to interpret. Restless sleep with frequent waking meant atmospheric instability. Weather would change significantly within 12 to 24 hours. Unusually deep sleep followed by difficulty waking indicated stable high-pressure systems that would bring clear, hot weather for several days. Sleep disturbances that included vivid dreams or night sweats warned of electromagnetic disturbances associated with approaching storms. Even their sense of taste and smell became weather forecasting tools. Changes in saliva production and taste sensitivity occurred before humidity changes, allowing forecasters to predict moisture increases or decreases hours before they became measurably detectable. A slightly metallic taste in the mouth often preceded lightning storms by 6 to 12 hours, caused by increased electrical activity in the atmosphere. Unusual sensitivity to smells warned of pressure changes that would bring weather system movement. But the most sophisticated aspect of Bedouin weather forecasting was their systematic integration of all these signals into comprehensive predictions. They didn't rely on single indicators. They developed mental frameworks for processing multiple information sources simultaneously and extracting accurate forecasts from complex combinations of signals. That a typical forecast process began with morning wind assessment, establishing the basic weather trend for the next 24 to 48 hours based on wind direction, temperature, and humidity. This provided the foundation, but experienced forecasters never stopped there. Throughout the day, they would continuously monitor animal behavior, noting changes in livestock positioning, bird flight patterns, and insect activity levels. These observations either confirmed the morning wind assessment or indicated that conditions were developing differently than initially predicted. Evening sky observations provided the final layer of forecasting precision. Cloud formations, star visibility, and moon appearance allowed weather readers to refine their predictions and establish specific timing for weather changes. A forecast that began as rain likely in the next 2 days could be refined to rain will begin tomorrow afternoon and continue through the following morning based on evening celestial observations. Nighttime physical sensations, joint discomfort, breathing changes, sleep quality provided the final validation and timing adjustment. An experienced weather reader might go to sleep confident that a storm would arrive sometime the following day, but wake up with joint pain that indicated the storm would hit by midday, or sleep peacefully through the night and wake knowing that predicted weather had been delayed by 12 to 24 hours. A systematic approach created weather forecasting accuracy that often exceeded modern meteorological predictions, particularly for local conditions. While satellite-based forecasting might predict general weather patterns across large regions, a skilled Bedouin weather reader could pinpoint exactly when weather would change at a specific location and exactly how long different conditions would last. The preparation that followed these predictions was equally systematic and precise. They knew exactly which valleys would flood during different types of rainstorms and which ridges would provide safety during various categories of sandstorms. They could calculate travel times between predicted weather events and identify the safest routes during different atmospheric conditions. Their weather knowledge wasn't just about prediction. It was about survival planning based on precise understanding of how different weather patterns would affect specific locations and activities. Modern meteorology has validated many aspects of this traditional forecasting system, but it has also revealed why it worked so well. Bedouin weather readers were essentially creating high-resolution, location-specific forecasts by combining multiple data sources and applying centuries of accumulated knowledge about local weather patterns. They were doing by hand what modern forecasting systems do with computers, processing multiple variables simultaneously to create accurate predictions for specific locations and times. Perhaps most importantly, they understood that weather forecasting in extreme environments requires constant vigilance and continuous refinement. They never made a single prediction and then stopped observing. Every hour brought new information that could confirm, modify, or completely change their forecasts. This adaptive approach allowed them to maintain accuracy even when conditions developed in unexpected ways, because they were always ready to update their predictions based on the latest signals from the desert itself.